So good morning. We have 14 students here. Let's get started. We were doing the H2 plus molecular ion problem. It is the simplest molecule type problems. And then it has one electron only, so we don't have to worry about electron-electron interaction issues. The question now becomes how one electron and two protons could bind together to form a stable molecular ion. If we understand that, then it's rather easy conceptually to extend it to the understanding of hydrogen molecules, H2 molecules, and many other molecules. So let's get on with our discussion of this H2 plus molecular ions. We are discussing about the electronic part of the molecule problem. We want to see binding. That is to say, how come this binding curve with a minimum and a preferred separations could emerge from quantum mechanics. We have a Hamiltonian, one electron, two centers, two protons. The separation between the protons is taken to be a parameter called R. Given one R, it is one quantum mechanics problem. So here we sketch what is the potential energy function solved by the electron in this problem. So when the two protons are very far away, it is just like two hydrogenic potential that has nothing to do with each other. So one on the left, one on the right. But when the separation is smaller, in the middle region between the two protons, negative plus negative is more negative. So here the potential energy function is actually lower, further reducing the separation in between, it is even lower. So that may be advantageous for one electron to live in a bigger space, so it could see proton number one and proton number two, and then do something about the wave function to lead to binding. And that is exactly the idea. So the key idea today is to introduce the most important, in my opinion, also the most physically transparent approach to understand molecules. I emphasize, well, it's my case, physically transparent is more important than mathematically rigorous in many situations. By that I mean, you can easily visualize what is happening in a molecule based on what we learned in atoms. So the method here has a shorthand, very famous terms called LCAO. The long form is linear combination of atomic orbitals. What for? To form the solutions to the molecular problems. The solutions are called molecular orbitals. Just like atomic problems, the 1s, 2s, 2p, you call them atomic orbitals of a particular atom, helium, say. So the full name, standard name in quantum chemistry and atomic physics and molecular physics is LCAO-MO. What it means is that we use this idea, LCAO, to form MOs. So we will focus on the discussion of this method in the first part of today's classes. At this point, it's useful to remind yourself of variational method. So if I have a linear combination as a trial wave function, immediately how many how many bases you use, you will form a size of the number of bases. So if you use 4, then you have 4 by 4. If you use 2, you have 2 by 2. And the matrix elements are standard, is of this form. We talk about it in week number 1. So if that doesn't ring a bell on your mind, then it is easier to think about the problem in a standard but simplified version. We could think about an atom as a finite well. After all, it has some discrete energies, just like 1s here, a p state here, and so on. And this analogy actually could take you very far. Now, if you have an AA molecule, you have 2 quantum wells put together, you may think about it as this problem, or even closer to our H2 plus problem in the middle, the barrier is lower. So if you are given this problem, you can solve it in 2 ways. Number 1, you call this places region 1, region 2, region 3, region 4, region 5. That's standard, right? And then you start to write down the wave function. So exponentially decaying, propagating in 2 directions, maybe decaying depending on the energy, whether it's lower than the barrier, and then propagating in both directions, decaying. Okay, then you have coefficients, you use boundary conditions, you have 1, 2, 3, 4 boundaries, you have 8 conditions, you should have enough equations to set up the problem. That is method number 1. What I meant is that this method number 1 just solve this new AA molecule problem as a new problem. You make no references to what you know about a single atom. But there's another way to do it. If I think about the left-hand side well as the left atom, I know the solution. So this is the ground state, this is the first excited state, and you know it well. The right atom, the same thing, so you know the ground state and the first excited state. Now, if you are given this new problem, the second method is to try to construct the solutions to this problem based on the known solutions of these single well problems, left and right. That is the key idea behind LCAO. So in this problem, we may as well say, if we want to solve this problem, the ground state say, I will write down a trial wave function. I use this first, the ground and first excited state 1 and 2 here on the left, 1 and 2 on the right. Therefore, I write a linear combination of all these 4 atomic orbitals, left atom, right atom. Now I'm using these 4 coefficients as variational parameter. Immediately in your mind should pop up a 4 by 4 matrix problem. The elements is of this form. You can set it up, then look for the eigenvalue, solve for the determinant equals 0. Then you will get 4 energies. The lowest one will be a very good guess at the ground state. That is what we meant by LCAO. It is this particular line. We are using the atomic states, left and right, choose a good number of them by physical insight, and then do this variational calculation in our mind only. We are not going to write it down explicitly, but you know the process. So this is the idea. Then comes some questions. How many atomic orbitals from each atom to use? Good question. The answers could be lazy. The more the better, of course, in principle. You use more on the left, more on the right. The matrix is bigger, or the basis is more complete or closer to completeness. But a better answer would be to be guided by physics. Because you know some atomic physics, thereby when two atoms comes together, you know rather clearly which atomic orbitals will be involved in forming the chemical bond. Now carry on with our simple example. If you are given such a double well problem, symmetric at the middle on both sides, if you are asked to sketch the ground state and a wave function, I think you may sketch something like that, right? First of all, no nodes. So that is ground state. Secondly, the potential is smaller on both sides, so higher probability of finding the electron makes sense. Well, in the middle, there's a barrier, so smaller probability makes sense. Then, from the middle, that is the right-hand side, and it is symmetric to the left-hand side, because with this symmetric well, if you stand on your side looking at the screen, then it is the front end, the front wheel. You can go to the other side of your monitor, then this is the rear wheel, and then my left will be that person's right, my right will be that person's left. So that we would expect the probability of finding the electron should be symmetric between the midpoint. So with all this idea, this is a very reasonable sketch. Okay, now if we look at the two atomic ground state, the left one, the right hand one, if we do a add linear combination, that is to say we just add them up, but different centers, all right? So ground state on the left, ground state on the right, you add them up, it's already quite like the ground state. So this is LCAO, do you see? Right? And this add with the same coefficient in front reflect the symmetry between the about the midpoint. That is to say, this coefficient shouldn't bias one side. The absolute value should be the same. Okay? Even if you sketch the first excited state, you would guess something like that. And that is quite like ground state on the left minus another linear combination. This is an odd combination about the midpoint. That is already quite like the first excited state. Okay, so this is the idea behind LCAO. And using these simple examples, it makes good sense already. Okay, so that is the big picture. All right, let's get back to our H2 plus discussion. So we have a hydrogen atom, atomic states on the left-hand side. We solve the hydrogen problem. We have 1s, 2s, 2p, a lot of them. Okay, let me call this set the atomic state from the left-hand side. So phi L is the left-hand atom, left-hand side one. I labels 1s, 2s, and so on. So this is the whole set. Similarly, I would have a big set from the right. I have a single electron problem to solve, H2 plus. The potential energy function is of this form, just to remind you. Now, by the idea of LCAO, we are to write the solution as a trial wave function to be a linear combination of atomic states on the left and atomic states on the right, each carrying a coefficient in front. So this linear combination of atomic orbitals is the starting point of LCAO exercises. Okay, so at this point, I will pause to see whether you understand the starting point of LCAO. Is everybody okay with this? Any questions up to here? Is it okay? Following? Now, up to here is very scary. This is a big set. This is another big set. Therefore, the matrix will be very big times very big, right? Then you may think, oh, hopeless, right? So we are going to be more practical when we go into H2+. But here, I would like to write down a general approach so that that could be generalized to many other molecules. For example, even polyatomic molecules, you have 3 atoms forming the molecules, you could add another term, okay? So let's continue. As I said, this is an art and a science. We should guide by our physical sense or physical insight. For our problem, H2+, 1 electron binding 2 protons, we usually are looking for the ground state, lowest energy state of this combination, this molecular ion. So it is difficult, hard to imagine what the higher atomic states will be doing in this bonding. For example, the left-hand side 3D orbitals and the right-hand side 3D orbitals, it is too high in energy. It is something like 11 eV or 12 eV above atomic ground state. So the energy is so high. By perturbation idea, they have little effect because the energy difference goes into the denominator. So practically, we could imagine that the higher atomic state would have little to do with the lower molecular states formation. Back to our H2+, it means, how about this? The simplest possible set will be to take 1s, the atomic ground state from the left, and then the atomic ground state from the right-hand side center, 1s from the right, and then form this simple linear combination. Only 2 terms, okay? Now in your mind, you should start your program, think about variational calculation, 2 terms, 2 by 2 matrix, easy to do, there are 2 energies, so on, okay? So that will be the simplest LCAO approach for H2+ and H2 molecule, actually, okay? So we understand that it is just 2 by 2 matrix, and 2 by 2 matrix mathematics has to do with pushing, right? One state will be pushed it up, one state will be pushed it down. It started to make sense to bonding. You have atoms coming in, 1s, 1s. When they are close enough, they start to push. One goes down, one goes up. You have only 1 electron. In this case, the electron goes to the lower one. It has a lower energy than 2 things separate. Bonding, done. Get me? Do you understand? Get the big picture, guys? Understand? That's why I asked you to do some 2x2 matrix mathematics in the first problem set. Now it is the place to use it. It is street fighting matrix mathematics at work. Now you are using it, okay? So let's get started with this very simple left, right, only one S. See how it forms bonds. Now there are two ways to go. One is to go mathematics. That is the left-hand side. I wrote a complete appendix to this calculation with all the formulas written down, and that is the left-hand side, okay? So you start with this. I called it 15152 just to go with the symbols that we used in chapter 1, approximation method. Here, 1 means the left-hand side 1s, this should be right-hand side 1s, sorry, I will correct it after class. So 52 is the right-hand side 1s, okay? Now you proceed with variational calculation, then the matrix elements are of the same form, therefore you need to calculate this H11. By symmetry, I think you have a sense that H22 is the same as H11 because they are the same atom, hydrogen. Now, then you need to calculate this S11, that is this times itself, integration. Then S12 is left-centered 1s, right-centered 1s, this and that, do the product, integrate over all space. This week, the TA will work this thing out for you. I think it take him 4 pages of integration, and turns out for hydrogen only, because we know the wave function, this can be done analytically, but rather laboriously. It can be done with an exact analytic expression, rather beautiful, but it is beyond exam purposes. But just to show you that that can be done, okay? So this all elements can be evaluated. Therefore, you can find 2 values for the energies. You plug in different R's, you see whether there's a binding curve. Of course, the answer is yes, because H2 plus exists. Another method is to go by physical sense. In the following pages, I will follow this path, but we will go back to this path. You will go back to this path in the appendix. Okay, so now I'm going on the right-hand side path by physical argument. It's just as rigorous. As I said, there's a symmetry about the midpoint because they are the same hydrogen. Hydrogen is hydrogen, okay? If it is hydrogen fluoride, then this argument on the right-hand side will not work. But the approach on the left-hand side still works, okay? Now I make use of the symmetry argument, and I know because of the symmetry about the midpoint, the coefficients, absolute values should be the same, just like my well 1D well problem. The reason is that I have a picture here, okay? So on the front side, I would say this is my left-hand side, but if you are standing on the rear side, you will say this is the right-hand side, right? So, but they are the same thing. So about the midpoint, the electron should not bias either the left-hand side or the right-hand side. The probability of finding the electron should be symmetric about the midpoint. So this is what I said about the symmetry. Now with this idea, there are only two choices. The coefficient either be the same, both are plus, 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 but they are same. I take it out, call it a C plus. So this is the plus linear combination. The other one is the coefficients in magnitude are the same, they're off by a sign. So one is plus, one is minus. Therefore, I took out the common magnitude, and then there is a minus combination. And these two combinations preserve the symmetry of the probability. I mean, wave function square, okay? So with this, we already know the linear combination, how they linear combine, and therefore what remains is to calculate the Hamiltonian's expectation value. That will be the binding curve, all right? So that is the two ideas giving us the same answer, the binding curve at the end. So let's proceed. So our tri-wave function is C1 phi 1, left hand 1s, C2 phi 2, right hand 1s. Here I want you to notice explicitly phi 1 is hydrogen 1s, but it is centered at a place called capital vector RA. That is where I put the A nucleus. Similarly, phi 2, centered at a different place. That is where I put the B nucleus. The separation between RA and RB is my R, the parameter, the distance between the two nuclei. Explicitly, what are they? Now, last term, you solve the hydrogen atom, but you put it in the center at the origin, 0, 0, 0. I look it up. The ground state wave function in this case is exponential minus R divided by Bohr radius and a normalization constant. The Bohr radius, let me remind you, is 0.5 something angstrom. So I just put it in half angstrom. Now, this is centered at 0, 0, 0. If I put it at A, how should I write down the 1s ground state? Normalization is the same. Only this place become R minus the distance from the nucleus. Okay, so here you have R minus 0. So you have this minus R. So this is the form of the 1s wave function decaying from a place called RA. Okay, this is explicitly what phi 1 is about. Similarly, phi 2 centered at RB. All right, so although we use shorthand to go with our previous notations, it is useful to remind yourself they have different centers, RA here and RB here, okay? Why I stress this point in our discussion? Here's the reason. On this method, we need to calculate various integrals. For example, H11, we are using phi 1. So we are using the 1s on the left to do the integral with the Hamiltonian in the middle. Okay, now that can be evaluated, see appendix. A more interesting one or simple one is this S11, S12, and S21, of course, is related to S12 and then S22. So let's look at S11. What does it mean? Okay. Now, one is this thing, center on the left. Another one is also centered on the left. So what does it mean? S11 is direct rotation. Doesn't mean anything. Now, this means more. Both 1s are centered on A. Now, multiply together, they form magnitude square. You integrate over everywhere. That is the probability of finding the 1s electron centered at A, regardless of the place. Of course, the electron exists. By normalization, is 1. Okay? So S11 is simple, and it is also S22. Here is a point that I would like you to take home. It is about S12 or S21. It doesn't matter. Now, formally, what is it? 1 is the 1s state center on the left. I should have put a complex conjugate sign, but I take 1s as a real wave function. Therefore, I don't need to do it. Then, what is 2? Now, 2 is a 1s, all right, but it is a different center, centered at B. Okay? In a pictorial way, it is the following. I have a left center, left hydrogen. You may think about that as such. Right hydrogen, each has a ground state that is exponentially decaying. The exponential decaying spatial extent is about a Bohr radius, half an angstrom on both sides. All right. So now, if R is not too big, for example, if this is 0.8 angstrom, you can imagine there is somewhere in the middle. Both wave functions are not 0. They multiply together, it's still not 0. You add up every places, then it is non-zero. That is to say, formally, this S12 as a function of R is not 0, although it's not going to be big. But it's not going to be big because, you know, there is only a region along the whole space that both functions are not 0, so that the product is not 0. Okay? Now, the key idea I would like to convey is the following. For one atom, when you solve the Schrödinger equation for the atomic orbitals, all these states belonging to one atom can be made orthogonal. By orthogonality, different eigenstate, the inner product, the integral is 0. That is strictly mathematical 0. Okay? Here, S12, 5152 are our bases. S12 is the inner product or the integral form by multiplying the bases together. Okay? There is nothing in mathematics, Hermitian, Hamiltonian, whatever, you look up in quantum mechanics, there is nothing that tells you about whether the atomic states from two different atoms, they are orthogonal or not, because they belong to different atoms. Okay? Now that is the point that I made in week number 1 when we do variational calculation using a basis. At that point, I say I don't assume the basis sets are orthogonal. And now I hope you can make connection. This is the place where this two bases, one S on the left, one S on the right, formally, they are not orthogonal. Okay, so I pause here to see whether you get this point. You get this point? I want to echo what I mentioned previously. Okay, now, although I emphasize in general it's not zero, but I would not like to give you the impression this thing is going to be big. No, it's not going to be big. Okay, now let me give you some number. At the end, this preferred separation is about 0.7 angstrom. Okay, so both sides are decaying, but in the middle, they do see each other non-zero. But the product is dropping times dropping. I mean, exponentially decaying times exponentially decaying is not going to be big. All the other places, for example, here, the right-hand wave function is not zero, but the left-hand wave function at this place, due to the exponentially decaying, is dropped to very tiny number. So the product is not going to be big, all right? So it's not zero in general, but it's not going to be big. Second point, if I put these two atoms far apart, that is to say, if I take this B all the way out here, okay, they are off by 5 angstrom. That now you know, half an angstrom, they exponentially decaying, okay, on both sides. Nowhere throughout the region, both can be non-zero. Therefore, this integral approaches zero as the separation become very far, very big, comparing to the ball radius. As I mentioned, this week, TA will evaluate this thing analytically, step by step, okay? Some cylindrical, you pick a good coordinate, you do the spherical coordinate integration. That can be done, okay? So this is a summary of what I just told you, okay? It is not zero in general, but it is not going to be big. And this S12 goes into here and there, okay? S21 is a cousin of S12. For real functions, they are the same, okay? So with all this, we can simplify our 2x2 matrix thinking. S11 is 1, S22 is 1, and then S12, I put it as S of R. So the matrix problem becomes something like this, okay? But we already argue it's not zero, all right, but it's tiny. How about this? To get a quick picture, ignore this, set it to zero, okay? It's not going to be big, but it's not formally zero. That's the point I want to make. Then you have this very simple situation, okay? Thereby, it is a 2x2 problem with identical H11 on the diagonal. It's like minus 13.6, minus 13.6 roughly. This is atomic state. Then it is H12 that is pushing. So remember, you have done something called epsilon, epsilon, delta, delta in your problem set, okay? The answer is epsilon plus minus delta, right? So one is push up, one is push down, all right? Now, you have the same, exactly the same situation here. So you have this, therefore, one is pushing up, one is pushing down. So you see, one is encouraging bonding. Now, you may think that this is higher, but at the end, this thing is negative because there are terms with negative sign in the Hamiltonian, okay? So what I'm trying to say is that far away, minus 13.6 eV, minus 13.6 eV, they don't care about each other's presence because their wave function does not sense the other atoms is around. Closer, they start to overlap, and with the Hamiltonian term, set up this 2 by 2, they start to push each other. One is lower in energy, that is the bonding molecular orbital. One is pushed up, that it will be called the anti-bonding. It's empty anyway. The electron goes down there, gained energy by doing this particular combination. Therefore, H2 plus is formed. So this is the street fighting mathematics that you have done. I anticipate the off-diagonal H12 to be negative. That's why I write minus delta. Therefore, this is the lower energy state. That will be the higher energy state. You can also solve for the eigenvalue, eigenvector. The lower one will be 1, 1. That is this to say the two coefficients are the same sign, same magnitude. I pull it out, that is called C plus, and that is the symmetry argument, what the symmetry arguments also gives. The other one, higher energy, the eigenstate is 1 minus 1. That is the case where the coefficients are the same in magnitude, but off by a sign. That is the case I call C minus, I pull it out. So either way, we got the same argument, okay? Same result, all right? So what I'm saying is that many pages ago, I advertised there are 2 ways to go. You can think this way, and then at the end, you get this thing as well. Nice. Now, I would like you to take another important concept home. If you understand this street fighting matrix mathematics, what is doing the pushing? The pushing is the key point in having bonds, because lower energy, gain energy, binding energy, okay? Now, it is the off-diagonal term that is responsible for it, H12, okay? If this is big, delta is big, one is pushed down more, the other one I don't care, okay? And more energy will be gained. So let's look at what is H12. This is the energy responsible for bonding. What is it? It is 1, 2. So on the left-hand side is the 1s centered at A. On the right, 1s centered at B. Different centers. In between, there's an H. Okay? So at this point, the take-home message is this is the integral responsible for lowering the energy. We will have more to say there. Okay? So I already mentioned this symmetry argument, and therefore we have only 2 cases. Okay, I'm doing the right-hand side argument on this page. Therefore, we get the same 2 linear combinations. Now, we can even obtain the normalization constant. What I mean is that, can we find this? Of course, you require this to be normalized, then you can get an expression for this, okay? So here is a 1-page derivation. So I require this to be normalized. 1, I write it out. This is left plus right. So I have a left times left term, right times right term, but I have 2 cross terms. Left times right, right times left. Taking real wave functions, they are the same, all right? Therefore, I have 1 plus 1. This is the thing I call S of R or S12. So these two are the same. Therefore, this square is 1 divided by 2 plus 2S of R. So we can even get the normalization constant. You can take the TA's answer this week for this, and then you know everything. You normalize it, okay? Similarly, C minus can be done as well. We use the symmetry to write it down, and therefore, we have this symmetry about the midpoint between the nuclei, all right? Now, I just would like to remind you, we are using the symmetry in this problem because it is homonucleus. I mean, both sides are the same. We will be discussing heteronuclei molecules, meaning A and B, they are different. In this case, you don't have this luxury of using this argument and get the C1, C2 so easily, okay? We are lucky. Well, intentionally, we pick a simple problem so that we can make use of that. So now let's look at some picture. When R is very large, we already mentioned it. This is phi 1. This is phi 2. Okay? You add it up, it's just this add to that. They don't actually meet because there's no place both wave functions are not 0. Okay? So it is just one add to the other one. Nothing to add actually. The minus 1 is the same. Minus this means flip it to the negative side. Wave function doesn't matter. Physical meaning is wave function square. Okay? So we have that. And now, even if you look at the probability square, the plus combination square, the minus combination square, they look the same. Okay? Now, that is the case. Large separation, for large separation. That is to say, no molecule form. They don't care. They are two separated entities. Okay? So this is what I try to depict here. They are so far away by many Bohr radius, therefore they don't care about each other, and there's no pushing effect. Because if you look at H12, this is this thing, this is this thing. Nowhere there's a region, they are together not 0. So this integrand everywhere is almost 0. There's nothing in the off-diagonal element, nothing to push the atomic states. More interestingly, we should look at the separation is around the bonding or the equilibrium separation region. By physics, we know atomic states is 1 angstrom or 2 in spatial extent. So 2 atoms come together. If their center is about 1 to 2 angstrom, they have a chance to feel each other's presence. So with this, if we look at R is 1 to 2 angstrom, it doesn't matter what value you use, you can plot it out. Now, here is the interesting thing. Pay attention. I have a left-hand side decaying, add to a right-hand side decaying, then in the middle, they are both decaying, but they add together, it start to rise a little bit. Okay, so this is the plus combination. To be contrast with the minus combination, we got 2 eigenstate. The minus one side decaying, another side decaying. By symmetry, At the midpoint, they decay to the same value, but they cancel each other, minus. Therefore, you see, in the midpoint, 0 is a must. The wave function must be 0 for this minus combination. Born interpretation comes in. Wave function square is the probability. Okay, wave function square. You see, the plus combination, we will call it bonding combination later for the reason we see the curve. Okay, you see, there's some enhanced probability of finding the electron near the middle of the two nuclei. I think that's what you learn in high school, right? But as you will see, what you learn in high school is not the whole story, okay? But at least in high school, you say you have this a silly picture. The electron lives in the middle. So using the Coulomb attraction of the left-hand nucleus, right-hand nucleus is stabilized the whole thing, okay? It looks as if electromagnetism works. Let me tell you, electromagnetism works in the Hamiltonian, but it is quantum mechanics that works for bonding. We will see, okay? Now, for the minus combination, it is 0 in the middle. Okay, you take this string square, it is absolute nothing in the middle. It is a note in quantum mechanics language in the middle. Okay, so no probability of finding the electron at the midpoint, and small probability of finding the electrons in the middle of the two, around the middle of the two nuclei. Okay, now that is a key difference between the plus combination and the minus combination. This is called the bonding one. This is called anti-bonding. It's not encouraging bonding. This encourages bonding. Here, I just put the two figures together on one page so that you have the full picture on one thing, okay? Now, very far away, the effect is not that big. Plus minus looks almost the same, but closer, 1 to 2 angstrom, there's a big difference. Good probability here, no probability there, okay? And now, one can solve this problem numerically without using LCAO, and that is done by Slater, the same Slater of the Slater determinant, okay? He wrote many books. I took this from this book, Quantum Theory of Matter. And here, he gives this figure in his book, solving the H2 plus numerically without using LCAO. So here, I just want to show you this wave function picture. Very far away, the solid line is bonding. The dashed line is anti-bond. The solid line is the plus. The dashed line is the minus combination. You see the dashed line here, and then it overlaps with this, the other side, okay? That is very far away situation. Closer, again, you see the plus one has some enhanced probability of finding the electron around the middle of the two nuclei. The antibonding one, dashed line is 0, and the shape is very close to what we just discussed using LCAO. Even closer is the same features, okay? So with this, I hope that you get the idea. LCAO makes good sense and it works, okay? So at this point, let's take a break, and then I will give you the binding, show you the binding curve due to the plus combination.